Good morning, dear students. Today we're having the ninth practical lesson that is about double integrals in rectangular coordinate system. Let me share my screen. Analogically to the one-dimensional, so definite integral, we have a region of integration. Actually, in one-dimensional case, the region of integration is just a segment, and here we have for double integrals two-dimensional region. And first of all, before we start calculating double integrals, we will have some practice for determining the limits of integration. And let's start with task number 1. So 1a, we have the following integral, double integral by region D, by variables x and y. So for now, it doesn't matter us which function do we have. So we just need to define limits of integration. So first of all, we have a rectangle. Actually, it is, so we have it on this figure. So x from 2 to 5 and y from 0 to 3. So how can we, so actually we have everything that can describe the region of integration, so we can write it in a following form. So integral will look like this. So from 2 to 5, first of all, we integrate by x, and then from 0 to 3, we integrate by y. Actually, in this case, we can use, so we can turn over limits of integration. So we can invert them. So we can integrate first by x. So integrate, so just outer inner integral, and so by x, and outer integral by y. So it so we can change it for the rectangular region. Any questions about this exercise? Okay, no questions. So let's move to part B. So we have another the region of integration. So now it looks like this. So what do we have actually? So y is greater. So y is greater than 0 and less. I square is less than 2x. So it is a parabola. And also y is greater than 0. Stop. Y is is less. Okay. Yeah, y is greater than 0 or equals 0. And x is from 0 to 2. So we have the following segment. Actually, yeah, the same we have here. So how can we describe the region D? So x changes from 0 to 2, and y changes from stop. How I guess it's better to Okay, let me check how better to describe it. So, well, I guess firstly it's a good idea, yeah, to define y as an outer variable. So y will be from 0 to x, as we see from the graph, and x will be from 0. Oh, stop. No, x will be from 1 over 2 y square to 2. Why we have here a function? Actually, yeah. So when we go from up to down, what's going on? I lost this tab. So uh, we define y as an outer variable. So we go from the top to bottom, and we just substitute numbers. And x depends on y. So we go from the left to the right. So we go from 1 over 2 y squared to 2. So the limits of integration will be the following. So from 0 to 2 dy, and inner integral from 1 over 2, 1 over 1 over 2 y square to 2, and the following integral. So any questions about this exercise?
Тобто верхній інтеграл ми розподіляємо як той, який протикається. Чи як?
Well, so you mean this integral, yeah? That is out of, so outer, not inner, right?
Yes, yes.
Well, we define which is inner or outer just as more convenient for us. We can invert uh, limits of integration or order of integration. So we can firstly define by y and integrate by y, then by x. And we will have more practice in the next exercise. So have I answered your question? Did I understand you correctly? Okay. So now we will change the order of integration in the following integrals, and it will be a good practice. So the first integral will be the following. Okay, let me erase it. And here what we will have, so y from 0 to 1, and x from y to square root from y. So we already have limits of integration. We need to change the order of integration. And how to do it? We have to plot the graph. So first of all, it's a good idea to plot the graph of this region. So x equals y, and x equals square root from y. So we have such a segment. So y changes from 0 to 1. We have it. And also x changes from y to square root of y. So we have such region. So we need to express variables in, so we need to invert variables. So we now express x as independent variable. So as we can see from the graph, x changes from 0 to 1. So x changes from 0 to 1. And by the way, it's a good idea maybe to use hotkeys. So from 0 to 1, and y changes from x square to uh, no, it changes from no, x squared to x. And now we can write down a new limits of integration. And yeah, don't forget to change variables of integration here. So exercise A is done. Any questions about this exercise? So usually it makes sense to define limits of integration just as it will be more convenient for you to calculate. It is the main idea. And now moving to B. So dx here will be dy, and let's write down new limits of integration. So from 0 to square root of 1 minus x square. So again, plotting this graph. As we can see, it should be semi-round. So y equals 1 square root of 1 minus x square. Yeah, so greater less or equals, let's write down like this, and also y is greater than 0. And we can see that x is from -1 to 1. So we need to express x via y variable. So yeah, and y just as an independent variable. So we can see that from this plot that y changes from 0 to 1. And what about x? Actually, this is a minus square root of y. Yeah, so we have different, so this is minus square root of y, and this is square root of y. So minus 1 minus square root of 1 minus y square, and so less than or equals than x, and less than or equals than square root with sign plus. So we defined limits of integration, and now let's rewrite them. So from 0 to 1 dy, and from minus square root to square root dx. So it's done. Any questions? I guess that no questions. Okay, and now more complicated exercise, more complicated case. So we have sum of double integrals, and this sum will be converted to a single integral. How? We'll see it. And first of all, we start with plotting a graph. 3 minus x over 2. So I will erase it. And it is 2c. So let's first of all plot all these curves. And we will see what we receive. So y equals x square. Then y equals 3 minus x. And 3 minus x over 2. Then, yeah, y is greater than 0. So y, yeah, let's write down y equals 0. And what can we see from this graph? So x changes from 0 to 3. So from 0 to 3. So we see it. And for the first integral, y changes from 0 to x square. And for the second integral, y changes from 0 to 3 minus x over 2. And now let's express x via y variable. So, yeah, first of all, yeah, let's look how y changes, and y changes from 0 to 1, as we can see. So, and what about x? So expressing variable x via y, so it will be this curve will be square root of y. And also we need to solve to express this where this expression where y. So this expression equals y, and x equals minus 3 minus 2y. So done with the limits of integration. So stop. 3 minus 2y. Yeah, not minus. And now we rewrite this sum of integrals like a one integral. So it obviously it's easier to integrate to calculate one integral rather than two integrals separately and then add them. So now limits of integration the following. So it's done. Any questions about this exercise?
About the second integral, or
Yeah.
I understand because we by the all on.
Sorry, this integral, what do you mean?
Yes, also integrate, but I understand that we cover all this figure.
Yeah, we cover all this figure, and this integral covers only this segment. But I don't understand clearly your question.
I mean that we also needed to integrate the second addend, but then I see that I was mistaken and
Ah,
we integrated.
yeah, so this is the... Okay, let me turn on an annotation. Yeah, so this is the regional integration for the first integral, this one. And this regional integration is for this one. And here we unite, for this integral, we unite them. And that's it. So I guess that no questions for now, right? or maybe no
Yes.
questions. Okay, so let's move next to the next exercise. So what we will do now, and now we start calculating double integrals. So 3a, so we will have the following integral. So x cube plus y cube dx dy, and the original integration is the following. So y equals x over 2, y equals x, x equals 4. Let's plot this region. And what can we see? We have such triangle. So limits of integration quite easy. So they're understandable from the graph. So x changes from 0 to 4. And y changes from x over 2 to x. So now we can start integrating. So writing limits of integration for x. And writing down this integrand. So now integrating by y. So analogically to differential calculus of a function of multiple variables, for now we x take as a constant. So x cube y plus 1 over 4 y cube, or y in power of 4, with the following substitutions. So from x over 2 to x. So writing down the following integral. So what do we have here? So x cube plus 1 over 4 x cube, or x, so x in power of 4 plus 1 over 4 x in power of 4 minus 1 over 2 y in power of 4 plus 1 over 64 y in power of 4. Oh, stop, not y, but x, sorry. Stop. Yeah, so everything is correct now. Yeah, we don't need these substitutions anymore. So now transforming all this expression, and yeah, let me just see what the common denominator, what will we receive? Stop, 1 over 32, but why 1 over 32? it's yeah, it's not correct here. So no, here what we calculate now, everything is correct. So mistake in my materials. So when calculating, let's see what we will receive. So So 64 plus 16 minus 32 minus 1. So 80 minus 33 equals 57 over 64. And now calculating this definite integral that remains. So 1 over 5 x in power of 5 with substitutions from 0 to 4. So actually here we will have 4 in power of 5. 4 in power of 5. 64 is 4 in power of 3. So we can cancel something. And we will have so 57 by 16 and over 5. And let's leave it like this. Let we not calculate it to the end. It is enough. Any questions about this exercise?
No questions.
Okay, no questions. Then calculating the next integral. Yeah, so the following integral. Okay, let's put it. Oh, let's first of all write down the integral. So y cubed by over x square dx dy. And yeah, let's first of all plot the graph. So y equals square root of x, y equals x over 3. Let's plot it. So y equals square root of x, y equals x over 3, and if I'm not mistaken, x equals 1. So we have such region. So let's first of all describe this region. So x equals changes from 0 to 1. And what about y? Y changes from x over 3 to square root of x. And now we can set up limits of integration. So from x over 3 to square root of x. By the way, in this case, we can also separate the variables, so a little bit. So for our convenience, we can move 1 over x square out of, so into the outer integral. Why? It is convenient. So now we will have only y variable here. So it is absolutely legal action. So now integrating by y. So 1/4 y cube, or y in power 4, and with the substitutions from x/3 to square root of x. So now, yeah, calculating. Okay, let's move to another line. So x square minus x in power of 4 over 81. So done it with it. And so only x remains. And now let's simplify a little bit this integral. So let's cancel 1 over x square. So we'll have 1 here and x square here. And now let's integrate. So 1/4 x minus x cube over 243 with the substitutions from 0 to 1. What's going on? So 1 minus 1/203. So now do we have 242 by 4 by 203. So let's simplify it a little bit. So it will be 101 over of 468. And it seems that we can simplify it even more. We can divide it by 3. So 141 by 3 will be equal 47, and 486 162. So that's it. Any questions about this exercise? Okay, I see that no questions, so let's move to the next exercise. So task number 4. So here it's not simplified, but okay. So now we have a task with application of double integral. So integrals just for integrals are useless, but now we will have some usage of some application of these integrals. We need to calculate the area of the region. So how to calculate it? So the integral is quite simple. So we just integrate. So the following integrate. We integrate just one in this region. So the first region is the following. So let's plot it. So it is bounded by the following straight lines: y equals x and y equals 5x and x equals 1. So y equals x, y equals 5x, and x equals 1. So we have the following triangle, and let's describe the region. So x changes from 0 to 1, and y changes from x to 5x. So now let's set up bounds of limits of integration. So dx, so from 0 to 1 dx, and from x to 5x dy. So yeah, let's write in details now. So we receive y with the substitutions from x to 5x. So it will be equal 4x. And now we integrate this expression, so we will receive 2x squared with the substitutions from 0 to 1. And it will be equal to. So this is the area of the region. And if we look at the graph, it looks like truth. So any questions about this exercise?
No questions.
Okay, no questions. And now let's see what else we can do. Okay, now let's have a break for 5 minutes. And after that, we will have more practice with the application of double integrals for calculation volumes, mass, static moments, and so on. And now have a rest. Let's continue. So we'll skip part B. Actually, it is analogical, but different limits of integration. But the idea is the same. So now we'll use double integral to calculate the volume. So we have the following. So the following body, it is bounded by cylinders. Yeah, let's move to Desmos 3D. So we have following cylinders. So y equals square root of x, and y equals 2 square root of x. Then so z equals 0, and x plus z equals 4. Let's make everything translucent, and we can see the body that is bounded by these surfaces. So actually, with the writing down all conditions with correct adjustment, we will see such a body. So so it is done, and also we can now we need to find the projection of this body on the plane x or y. So how to do it? We need to find the we need to find where these planes are intersecting. So we need just to solve equation. So here z will be equal 4 minus x. So 4 minus x equals 0. So then x equals 4. And now we are plotting their projection. And x equals 2. Oh, stop. Y equals 2 square roots of x, and x equals 4. So here is a projection of the body. So how to calculate the volume? We need to we need to integrate this the function that describes the surface that is on the top. So this plane. We need to integrate this function on by the projection. So we express z via x. So x minus 4 dx dy. So the following integral. And now let's describe the projection. So x changes from 0 to 4, as we already defined. Then y changes from square root of x to 2 square roots of x. So let's integrate. So from 0 to 4 dx, and from square root of x to 2 square root of x, x minus y, or x minus 4 dy. Integrating. So what do we have here? X minus 4 by y. With the substitutions from square root of x to 2x. So 2 square roots of x minus square root of x. So now multiplying everything. So x square root of x minus 4 square root of x. So 2 over 5 and x square by square root of x minus 8 over 3 x square root of x, and from 0 to 4. So let's substitute. So 2 over 5 by 16 by 4 minus 8 over 3 by 4 by 2. So let's calculate it. So 128 over 5 minus 64 over 3. So yeah, let's find the common denominator. 382 minus 320, and it will be equal 64 over 15. And let's check it with my recordings. Yeah, 100. Stop. Why 65? So yeah, something is some mistakes here. And why 2? Why? Yeah, 2. So it is a mistake here. So 64 over 5. But it's something, yeah, it's not correct because it is less. So let's check what is going on here. So 64. Stop. Why? Yeah, it is. Stop. 4 minus x. Damn it. 4 minus x everywhere. It was my mistake. Yeah. So everywhere the sign is incorrect. Oh, I'm sorry, just a moment. Okay, let's continue. So, x 64 over 3 minus 64 over 5. So, well, actually, so we have, what do we have here? So another, yeah, common denominator. So, yeah, it will be equal 64 over 15. Oh, I don't, so let's, yeah, 128 over 15. So, that's it. Any questions about this exercise? Okay, no questions. So moving to the next task. So now we have to calculate the mass and average density of a plate. And it is bounded by the following lines. So y equals x squared and y equals 1. The plate is already, so we can see it is plotted here. And how to calculate the mass? Mass is calculated by the following formula. So we calculate the following integral by d. So we calculate the density. We integrate the density by dx dy in this region. So in our case, it is x squared plus y squared. And let's also write down the limits of integration. So as we can see from this graph, x changes from -1 to 1, and y changes from x squared to 1. So let's integrate it. So what do we have? So the following integral will be the following antiderivative. So x squared y plus 1 over 3 y cube with substitutions from x squared to 1. And now substituting, so what will we receive? So x squared plus 1 over 3 and minus x in power of 4 plus 1 over 3 x in power of 6. So actually this is our integrand. By the way, we can see that this function is even, so we can simplify our calculations a little bit. So in this way, and then yeah, let's expand brackets in this integral and simplify what we can simplify. So x squared plus 1 over 3 minus x cubed minus 1 over 3 x in power of 6. So expanded with correct signs, and now we can integrate. One over 3x minus 1 over 5x in power of 5 minus 1 over 7x in power of 7 with substitutions from 0 to 1. And so 2 multiplied by so 1 over 3 plus 1 over 3 minus 1 over 5 minus 1 over 7. And what does it equal actually? Okay, let's believe this recordings, this record. So stop y 100. Yeah, I lost this 1 over 3, so 1 over 21. So the result is 88 over 105. Okay, so found the mass. And now how to find the average density. The average density is found by the following formula. So we divide mass by the area. So we also need to find the area of this region. So let's copy and paste a little bit. So we have the following integral. So now we have from -1 to 1 1 minus x squared dx. Again, this function is even, so we can simplify a little bit our calculations. And what do we have? So the following result: 2 over, multiplied by x minus 1 over 3x cube from 0 to 1. So 1 minus 1 over 3, and it is actually 4 over 3. So the average density is the following. So 88 over 105 by 3 over 4. And yeah, so it will be equal 22 over 35. So that's it. Any questions about this exercise? Oh, stop, S, not D. So I guess that no questions. Okay, let's continue. So now we have to find static moments with respect of coordinates axis and center of gravity over a uniform plate. It is bounded by the following curve. Y equals sine of x, and x changes from 0 to 5. So now let's calculate. So how to solve it? Actually, we need to do the following stuff. So when we calculate the center of static moments, we use the following functions. The following formulas, just let me remind you them a little bit. So the static moments are calculated by the following formula. So for axis x, so if we calculate static moments with respect to x-axis, we use the following integral. So mu from x y dx dy and multiplied by y variable. And for static moments with respect of to axis y, so vice versa, we calculate, so we multiply by x-axis. Then what about the center of coordinates? So the following coordinates of the center mass, we have the following formula. So we do so the integral the following integral by region D divided by the area. So for x and for y, the following. So that's it. So we have all formulas. So now let's move to our calculations. First of all, let's describe the region of integration. So as we can see already from the graph, so x changes from 0 to p, and y changes from 0 to sine of x. So now let's calculate the integral. Let's calculate all integrals. In our case, mu from xy equals 1, so it is a constant. So our task is simplified a little bit, or maybe even not a little bit. So the task is the following for now. So x from 0 to p dx and integral from 0 to sine of x y dy. So the integral will be the following. So y 1 over 2 y square from 0 to sine of x so we have the following integral. So 1 over 2 sine square of x, and the integral is from 0 to p. So now let's modify a little bit this integral. So what will we have? 1/4, and here in the brackets, so 1 minus cosine of 2x. So we will have the following antiderivative. So x minus 1/2 sine of 2x from 0 to p. And we have p/4. So calculated the static moments with respect to x-axis. And now moving to y-axis. So we have the following integral, but we integrate x here in this case. Let's also move x here to the outer integral, and we will receive so x multiplied by sine of x dx from 0 to p, and now we'll remind a little bit integration by parts. So u equals x, du equals dx, then y equals dv equals sine of x, and v equals sine of x dx, and v equals minus cosine of x. So minus x cosine of x from 0 to p plus integral of cosine of x dx. So what do we have here for this part? Minus p multiplied by -1. Cosine of p is -1, so p, and here p minus 0. And here the antiderivative is sine of x with the substitutions from 0 to p. That will be equal 0. So the answer is p. So we found the static moments. And now what do we have to do? We have to find the area. The area is can be found by the following formula. So we integrate 1 so it will be integral over sine of x dx, and the result, so the antiderivative minus cosine of x from 0 to p. So -1, so equals 2. The area equals 2. So in this case, x coordinate of the center of mass will be equal p/2. And for this, so p/4 multiplied by divided by 2, p/8. So it's done. Yeah, if I'm not mistaken, everything is found that we had to find. So any questions about this exercise, about the whole lesson, about previous lessons, other questions?
No questions.
Okay, if no questions, have a nice day, stay safe, goodbye. Thank you for your attention.
Thank you.
Goodbye.
Bye.
Thank you. Bye.